Hi everyone. In the last lecture, we learned about how to multiply a matrix times a vector, and we saw that this gave us a new perspective on how to think about linear systems. In this lecture, we're going to learn about a different way to think about multiplying a matrix times a vector, and it's going to give us yet another perspective. So let's suppose we have a system of equations like this. We could interpret each of these equations as being a component of a vector. So basically that means that we can collect the three equations together into a single equation involving vectors. And now here's the real interesting part. Because the left-hand side involves adding and subtracting, we can actually decompose the left-hand side as a sum of three vectors, like this. And now you'll notice that in the first vector we can factor out an x1, and in the second vector we can factor out an x2, and in the third vector we can factor out an x3. And then you get an equation that looks like this. And this is something that we can actually interpret sort of geometrically, which is to say that we have these three vectors, 2, 1, 4, 3, 4, minus 2, and minus 1, minus 7, 6. And when we solve this system of equations, what we're trying to do is we're trying to find scalars, x1, x2, and x3, such that when you multiply these scalars times the vectors and add them all together, you get 5, 10, 8. One way that I like to think of this is as if there's a machine that has three knobs on it, and one knob controls how much 2, 1, 4 you have, another knob controls how much 3, 4, minus 2 you have, and then the third knob controls how much minus 1, minus 7, 6 you have. And then the question is, what should you set the machine to so that you get 5, 10, 8 as the output? And later on, we'll also have a nice geometric way of interpreting this. So let's just focus on the left-hand side of the equation we were just looking at. From what we learned before, we know that this can be rewritten as a matrix times a vector. And now, from what we've just seen, we know that we can rewrite it in yet another way as a combination of vectors. And I just want to point out that if you're at all skeptical of what I just did, you can do these calculations yourself just to make sure that it works. You can multiply the matrix times the vector in the middle, and you can do the vector addition and scalar multiplication on the right, and see that you actually do get, in both cases, the same thing that's on the left. Okay, so now the thing I want you to observe is that these vectors that appeared just now, 2, 1, 4, 3, 4, minus 2, minus 1, minus 7, and 6, those vectors are the columns of the matrix. And so what just happened is an illustration of a general fact, that if A is a matrix with n columns, and if we label those columns v1, v2, v3, and so on all the way up to vn, and if we write x as the vector whose entries are x1 to xn, then A times x is x1 times v1 plus x2 times v2, and so on, all the way up to xn times vn. So this is the column picture, because it gives a description of A times x in terms of the columns of A. You can compare this with the row picture in the previous lecture that described A times x in terms of the rows of A. And it's really useful to have both of these pictures because they're useful in different ways. I would say that the row picture is more useful for actually doing the calculations. Like if I'm multiplying A times x, then I'm going to be using the row picture to do the calculation. But I feel like the column picture is more conceptually useful. It helps me to understand better what's going on when I'm like solving an equation involving A times x, or trying to understand what does it mean when A times x is equal to something. I'm thinking in terms of the column picture. So this brings us to some terminology. Suppose you have a bunch of vectors, v1 to vn, that are all the same dimension. We'll just call that dimension m, just to give it a name. Then we can use these operations of scalar multiplication and addition to produce more vectors. And the most general description of what you can get looks like this, where every vector is multiplied by a scalar, and then you add all of the things together. The vectors that you get in this way are called linear combinations of v1 to vn. And hopefully you already see some connections to what we've been talking about before, but I just want to spell them out really carefully here. So first of all, there's a connection to matrices, which is that if you have a matrix A and you multiply it times a vector x, then the result is actually a linear combination of the columns of A. This is exactly what we just saw in the column picture, where we saw that if the columns of A were v1 to vn, and then if you write the entries of the vector as x1 to xn, then the multiplication is exactly a linear combination. So the next thing is linear systems, and we knew already that a linear system could be rewritten as a matrix equation, ax equals b. And then based on what we just talked about, we know that ax could be viewed as a linear combination of the columns of A. So this gives us a new way to think about linear systems, that when we're solving an equation ax equals b, what we're trying to do is we're trying to find all the different ways that you can express b as a linear combination of the columns of A. And so when you think about the different outcomes that could happen, you can interpret those in terms of this question. So like, let's say that there are no solutions to the system. Then that means it's impossible to express b as a linear combination of these vectors v1 to vn. Or let's say that there's a unique solution. Then that means that there's exactly one way to express b as a linear combination of v1 to vn. And then there's the possibility that there's an infinite number of solutions, in which case there's an infinite number of ways to express b as a linear combination of the v1 to the vn. So this interpretation is going to be something that's going to come up quite a bit later in the course, but it's good to have this terminology right now and to have this picture in your head. And then finally, there's a nice geometric picture that goes along with this. So let's just say you have two vectors, v1 and v2, and I'm drawing the picture as if it's in the plane, but even in higher dimensional space, two vectors will sort of determine a plane inside of that higher dimensional space. And so you can imagine that we're just looking at that plane in the higher dimensional space. And then you can use these two vectors to form a grid, as I've done here. And the idea, like in my mind, what I think of is that it's sort of like we're using these two vectors as the axes for the plane. Like we're forgetting the original axes, and now we're using these two vectors as the axes. And so this effectively gives us a system of coordinates on the plane, where, for example, this point is v1 plus v2, and so you can sort of think of it as 1, 1 in this new coordinate system. And this yellow point that I just drew is minus v1 plus 2 times v2, so you can think of it as being like minus 1, 2 in this new coordinate system. And so if you think back about linear systems, where suppose that you had an equation like x1 v1 plus x2 v2 is equal to b that you're trying to solve, you can think of that as trying to find the coordinates of b in this coordinate system that's determined by v1 and v2. And I'll point out that even though I've just showed you the picture when there's a system of equations with two variables, the idea is basically the same, but in 3 dimensions when you've got 3 variables. And even though it's difficult to visualize, you can really get some intuition for more variables just by thinking about the 2 and 3 variable cases and proceeding by analogy. So we'll be talking more about this later, but I just wanted you to see that this is a geometric picture that's actually quite different from the geometric picture that we were talking about earlier, where we had intersections of lines and planes. And it's useful sometimes to be able to go back and forth between them. But actually in practice, this is the geometric picture that people will use most commonly when they're thinking about linear systems. And so we're going to be focusing more on this than on the intersection picture later.